In the previous lecture, I worked out the case where we looked at the electric potential in what's called the retarded time. So what we've said was that at a time earlier, t sub r, that's the time now that I'm making the measurement minus the time it took for the information to travel from the charge to where I am making the measurement. And what I found is that writing out the potential in the form of essentially what looks like a Coulomb's law, except for now I'm writing the charge in terms of its past time. And the same is true for the magnetic potential. So measuring the magnetic potential now I could do that by integrating over the current as it was, like so. And what I found, at least working out the case for the electric potential, is that when I do that, if I take the second derivative, what I find is that the D'Alembert of V just works out to be minus the charge distribution as it is now divided by epsilon naught. So that I get the same equation back. So starting with a distribution in the past, I integrate over all space, and then what I find is I get this wave equation for what it looks like currently. Okay, and so the interesting thing is we don't have to necessarily consider the retarded time. That's kind of easier to think of conceptually. We could think of it as an advanced time, or basically measuring now and calculating what is going to be in the future. So the advanced time, the future, is the time now plus the distance and the time it takes for that information to travel a certain distance. And what you find is if I write the potential, the advanced potential, so measuring the potential at a location R at some time now, I could then calculate that as a Coulomb's law for a charge distribution in the future. And what you would find is that you would get the same result. Now it's a little harder to think about what is my charge distribution going to look like in the future, or my current is going to look like in the future at some future time, but mathematically we can still solve the problem. We can solve the problem as the charge distribution, what it was and what it's going to be now, or what it is now and then what it's going to be in the future. So if we knew the future distribution, we could calculate our measurements now based on that. So it's just a mathematical thing that is possible. Okay, so what I want to do now is look at an example. So I take a look at the example 10.2 in the book, and what you have is an infinite wire that carries current that looks like this. It's a time-dependent current that at a time right now, it's 0. And then at some time later, it's going to be a constant I naught. So right now, the current is 0. I flip the switch, and from now on, in the future, the current is going to be some constant I naught. So what we want to do is find the fields. Okay, so if I was to draw the picture, let's say we put the current on the z-axis. So here's my infinitesimal amount of current, like so. This is some distance s, This is some distance z, and the difference between where I'm measuring at S is r. So now I write out the magnetic potential at the distance S right here at some time t, and what I would how I would do that is mu naught over 4 pi in the direction of z, integrating from minus infinity to infinity of a current at some retarded time tr over r dz. So this is not going to be a volume current, but it is a line current. So I only have to integrate over the line dz. Okay, so at time less than S divided by C, the current is 0. At time greater than S divided by C, what I have is a position Z, which is less than or equal to the square root of CT squared minus S squared. It's basically the hypotenuse of that triangle. And the current is I naught. Okay, so let's put that into our equation. So A is now mu naught I naught over 4 pi in the z direction times 2, because it's a symmetric case, and we're integrating from 0 to a distance of ct squared minus s squared and dz over r, which is the square root of s squared plus z squared. Okay, so now I'm writing everything in terms of s's and z's. Okay, so we can look up this integral, the integral of 1 over the square root, and what you would get is essentially the natural log of the square root of s squared plus z squared plus z integrated in the limits of 0 to the square root ct squared minus s squared. So I know that's hard to see. So now if we apply the limits, then what we get is mu naught I naught over 2 pi, the natural log of, if I put in the, for z, if I put in the limits, then I would get, let's see, s squared, z squared would give me plus ct quantity squared minus s squared plus the square root of ct squared minus s squared. So that's the first one, minus the natural log. Okay, when z is 0, I would just get the square root of s squared, so I would get s, like that. All right. Okay, so we can combine those two natural logs. So all of that is in the z direction. Okay, so we can combine the difference of logs is the log of the quotient. So we would have mu 0 I 0 2 pi the natural log of ct quantity squared plus square root ct squared minus s squared over s in the z direction. Okay, so now we know the magnetic potential. We can plug it into our equations, and what we get is E, the electric field, is minus the change of the magnetic potential with respect to time. So if we plug that in, we get mu 0 I 0 C over 2 pi square root CT quantity squared minus S squared. All of that in the Z direction. So that's our answer for the electric field. For the magnetic field, you would have to take the curl of A. And when you do that, what we would get is minus A in the Z direction with respect to S in the phi. So that's the only one that, because basically A is only in the Z. So when you take the curl, the only thing that you would get is this derivative of the Z component of A with respect to S. So if you do that, if you evaluate that integral, you get mu 0 I 0 over 2 pi S times CT over the square root CT quantity squared minus S squared in the phi direction. So now we've got our magnetic field. We've solved for the electric field. We have both of those components. So what you would notice is that at a time t goes to infinity, the electric field becomes 0, and magnetic field becomes mu 0 I 0 over 2 pi S in the phi direction, which is essentially the static case. So what we have is a wire where we now turn on some current. So you now have some current flowing through this wire, I naught, and the moment that you turn it on, you're going to get an electric field which is pointing in the Z direction, like this, and you're going to get a magnetic field which is wrapping around in the phi direction. But what you find is that after you turned it on, it eventually settles into a constant current. If the current is constant, that's essentially the static case. And so if it's a static current, the electric field goes to 0, and what you're left with is the case of a magnetic field around a constant current, which you could essentially solve for with Ampere's law. But it's good to know that this whole derivation that we did, which was time dependent, eventually settles on to the static case, the time independent fields, ones that we studied in previous chapters in the book. So that gives us some confidence that we know what we're doing in solving for these electric and magnetic fields. What's even more interesting is that now we're actually in this kind of more realistic case where before we just had this constant current, and we never considered turning it off, turning it on. We never considered what would happen to the fields if you were to turn on a current and then turn off a current. And if you were to flip on the switch and you started the current, you should get this electric field, which should eventually die down to 0, but the magnetic field will eventually reach a constant value.